This is a tutorial to develop the dice fighters simulation in Python, as discussed in lecture. Now, if you remember back to lecture, we identified two main structural objects in the dice fighters game. I'll just start writing them here as a comment so we can guide some of our script development. First, we identified that there's an object called a battlefield, which has inside of it a counter for what round number, which is an integer. And it also had a behavior to advance the round. On the other hand, the other main object that we were considering were teams, where a team has a name, which is a string, team size, the number of dice fighters that are active, which is an integer, and a chance of hitting the opponent, which is a floating point number. And the teams have as well a couple of behaviors. They can compute the number of hits, which which returns an integer of how many hits does a team have on its opponent. And there's also a behavior to suffer losses, which subtracts a certain integer number of forces from their team. So this tutorial will be developing this dice fighter simulation. I'm going to save the script here as example dice fighters. And I'm essentially going to be replicating this desired structure in Python as Python objects. The one thing I didn't mention, though, was the interaction or the relationship between these two. That each battlefield also is associated with two teams. So each one battlefield has two teams, the red team and the blue team. Okay. So in Python, we represent these concepts using classes. So class is a description of a type of object. We have two classes here. This will be one for a team and one for a battlefield. So I'm just going to lay the outline of the code right now. I'm going to have a class for team. I'll just fill in a placeholder pass for now, and a class for battlefield. And inside each of these classes, the primary function or the primary thing we have to identify is the initializer. How do we initialize objects of these classes? And that's using the keyword def. We want to define a new function with a special name underscore init underscore, and then the self reference as the function argument inside of left and right parentheses. So I'm going to copy this initialization function into these two class definitions, and we'll start adding in the other attributes. Now the first thing, just starting from the top of this list, working the way down, we know that the battlefield needs something called a round number. So here in the battlefield object, when it's being initialized for its own self, we're going to create a new state variable named round number. And we'll say that all the battlefields start at round 0. So I'm going to give it an initial assignment of 0 here. The other thing we need to identify is each battlefield needs a behavior or a function called advanced round. So I'll add that in as a new definition of a function. The function name is advance round, and it uses the self reference as well. I'm not going to fill in the body of this method just yet, so I'm going to use this placeholder pass right now. Next thing is we need to assign each battlefield. Each one battlefield has two teams named red team and blue team. So inside of the initialization for battlefield, in addition to the round number, I'm going to give it a red team as a new team, and then a blue team as a new team. We'll worry about some of the specifics about if these initializers need any parameters a little bit later. All right, then working our way down further, we know that the teams object has 3 state variables. So we'll define those in the initializer. They need to have a name, which is some name. Maybe we can just give it a placeholder new team for right now. They need a size, and maybe we'll just give a placeholder of 10 for right now, for 10 dice fighters. And they need to have a chance of hitting, which will give a default value of 1 out of 6. Now it's important in Python that whenever you're giving fractions in code, that you make sure that you cast or otherwise identify one of the 2 numbers as a floating point. That's why I use this decimal point here. If, for example, I just use 1 out of 6, the response that it gives is 0, because what it does is rounds this result to the nearest integer, and so the result of 1/6 rounded down yields the result 0. If, however, we use 1 point divided by 6, gives us the nice floating point result that we'd expect. So keep that in mind when you're writing fractions in Python. Use the decimal point to notify that this is a floating point number. All right, the other 2 pieces that are missing are a function for teams to compute hits. Define a function named compute hits. I'm just going to have this pass. Don't forget the self argument. I'm just going to have this pass for now. And the same for define a function to suffer losses. And this one we know is going to require an argument, the number of forces to lose, and I'm just going to give that a variable name opponent hits for now, and otherwise we'll fill in the body of this later. Okay, so we have a sketch of how our program is looking so far. We have a team defined. Teams have names, size, chance of hits. They can compute hits, and they can suffer losses. And a battlefield has a round number, red team, blue team, and a function to advance to the next round. Let's do a quick test script to make sure that this is all working right now. I'm going to use the nice notation to only run this code if this script is being run as the main file. So I'm going to do a check to see if the name, global name variable is underscore underscore name underscore underscore. And just to do a quick check, say print OK. So with this script, I'm just going to run it real quick. In Spyder development environment, we get the OK flag, so everything looks just fine. So in our test script, the primary thing we want to do is create a new, or instantiate a new battlefield. So I'm going to create a new variable, battlefield, and assign it to be a battlefield object. And if we run the script and then investigate this over in the console, we see that indeed the battlefield variable is linked to a battlefield instance at a certain memory location. We can check that that battlefield has a round number. Indeed, it's 0. Make sure that it has a red team. It does. It's a team instance at a different memory location. Make sure it has a blue team. Indeed, it does. The blue team is also at a different memory address from the red team, so that's very good. And let's just make a check that the blue team has a name. Okay, it's reporting that it's a new team. In the console, you can press the up arrow key to go to your previous instructions more quickly. You can check to see if the blue team has a size. Indeed, it does, 10. And the blue team's chance of hitting is 0.16 repeating. Okay, so now we're ready to start implementing some of the details of the logic of this model. First thing we want to do is start to customize differences between the red team and the blue team. We know, for example, that the red team should have 20, while the blue team has 10 fighters. We know that the red team has a 1 out of 6 chance of hitting, the blue has a 3 out of 6 chance of hitting. We probably also want to change their names. So the easiest way to assign all of these model attributes or state variables is to add them as extra arguments in the initializer. So within the team class, when it's being initialized, we want it to specify maybe the team's name, the number of fighters, and their chance of hitting. Now these arguments, you can call them whatever you want. So maybe if I wanted to name this probability of hitting, that's perfectly fine. These are just placeholder names that we're going to be used to identify the arguments. Then when this initializer is actually running, we want to use those arguments to override the state variables, the name, size, chance, hits. And it's okay if the argument variable names, like number of fighters, doesn't exactly match the underlying model attribute, like size. We just have to make sure that we keep them straight in our head. It's usually a better idea if you do use consistent names. So just to keep this consistent, I'm going to change it from number of fighters to size, and from prob hit to chance hit. Right, so if we try to run this file now, we see that there's some errors that get generated. Over here, the console is saying that when we're trying to initialize the team within the battlefields, the red team, which just happens to be the first one we're initializing, caused an error because the initializer now takes 4 arguments instead of the 1 that was given. So when we were using it before, we were implicitly providing the self argument, but now we have to explicitly give the other 3 arguments. So give it a name of the red team. There's 20 initial fighters, and it has a 1 out of 6 chance of hitting. Similarly, for the blue team, give it the name blue team. It's 10 fighters, but it has a 3 out of 6 chance, keeping sure to get those floating point numbers specified correctly. All right, so let's rerun this file. No more errors. We can check that the battlefield .red team .size is 20. Looks good. Red team hit chance is, not there. That's because we called it actually chance hit is 1 out of 6. Same for blue team. It is 1/2, which looks good. Right, so we have the main state attributes specified, and now we can move on to filling in these functions to transform the state variables or perform state changes. So the first thing I'll do is actually the easy one, to suffer losses for the teams. We know, for example, that when teams suffer losses, all that really happens is that their size decreases. So if the opponent scores, let's say, 5 hits, we know that we have to reduce this team size by those 5 values. So the easy way to specify this in one line in Python is to access the self.size variable, and we want to simply subtract the number of opponent hits from it. So this notation minus equals means to take the current number of size, subtract opponent hits from it, and then reassign it to the same variable. So it decrements the size by some value. And we can test this out in the console. We can run the script to update the console. We can see that the battlefield.blueteam.size is 10. And we can try to run the suffer losses of 2 for the blue team. If we reinspect the size, now it reads 8. So it appears that the suffer losses function is working correctly. Now the other one, this compute hits, is a little bit more complicated because the number of hits that a team scores depends partially on random numbers that are generated. So Python by default doesn't provide random number generation, but we can import a separate package to allow us to perform those operations. And specifically in this example, I'm going to import a package called Numpy. So Numpy is short for numerical Python. It's a library that provides many useful functions, both for generating random numbers, but also for building and using arrays in an efficient manner in Python. So just to make this a little bit easier, since I'll be using Numpy a lot later in this class, I'm going to import the Numpy package, but I'm going to call it NP. So whenever I refer to this Numpy package, I can use the shortened version NP, which is what this import Numpy as NP statement means. So in this compute hits function, what I want to do is I want to generate a number of random numbers, so ideally probably between 0 and 1, and we want to generate one number for each fighter that's left in this team. So just to try this out real quick, I'm going to, rather than actually doing the computation, I'm going to print the result straight to the console so we can test it out. The Numpy function that we're going to use is in its random subpackage. So I'm going to access Numpy through the word np, np.random. You can see that the tool tip that expands down below gives some options. And the specific function that we want to use within random is the rand function. If you are curious about the documentation for these functions within within Spyder, you can select one of the functions and press Control-I. So Control-I will open over here in the Object Inspector. And this tells us, for example, that this rand function gives random values in a given shape. And the shape is specified in these arguments. So specifically, the dimensions, d0, d1, all the way through dn, are the dimensions of the returned array. So in particular for this case, we want some random numbers that correspond to the number of dice remaining, which is in the size attribute. So numpy.random.rand pass in as an argument the number of dice fighters that we have left, which is the team size, and we'll just test this out. So I'm going to rerun this script to reload it over in the console, and I'm going to go up here to the blue team, battlefield.blueteam.compute hits. Right. So again, this doesn't actually perform the function yet, but I have it printing out the result of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 random numbers. Blue team has 10 dice remaining, so it looks good. Now to actually compute the number of hits from this, though, we want to determine how many of these random numbers are less than the chance that the blue team has to hit. If the blue team has a 50-50 chance of hitting the opponent, then it looks like this would correspond to 1, 2, 3, 4, 5 hits. So 5 of these values are less than 0.5. We can implement that in code by storing these random numbers in a new variable, call them attacks, for example, and then computing and returning as the result of this function the sum of these attacks which are less than the blue team's chance to hit. Now this is a very short notation in Python, but we can test to see how it works over here in the console before we actually run it. So just as a test, I'm going to create a new variable. Test is np.random.rand. Let's generate 10 random numbers. You can see that those are stored in test. Now these are a new set of 10 random numbers, so we won't get the exact same result as before. But if we use an operation like test less than 0.5, we can see the result of this very short command is an array of booleans. So booleans are variables that are either true or false. And for this particular set of numbers, we can see that 1, 2, 3, 4, 5 of them are true and 5 are false. In Python, we have the very nice ability to sum Booleans to get a numeric result. So the sum of the values where test is less than 0.5 gives us 5 in this case, because there are 5 true values. Now over here where we implemented it, we are summing the number of attacks. Again, the attacks were those randomly generated numbers, where those values are less than the chance that this team has to hit. So let's see if this actually works in practice now. So I'm going to rerun this script, take a look at the battlefield.blue team, and this time we're going to have them compute hits. So for this particular run of compute hits, the returned value is 3, meaning that of the 10 dice, 3 of them met the criteria for the blue team to consider a hit. If we run this again, we get a completely different number. We could run this many times, for example, to get different results for a different number of rolls for the blue team. We could do a similar thing for the red team as well. Now, the red team has the different team size, the different hit probability or hit chance. So these random numbers, or the computed number of hits, is going to vary slightly from the blue teams, but nevertheless, it seems to be working. So with that, we have the behaviors programmed for the team. So we have, again, the 3 state variables, aim size and hit chance, or chance hit. Then we have these 2 behaviors, one to compute the number of hits based on a random roll of dice, and then one behavior to suffered losses. Now in the battlefield is where we actually connect these behaviors together to form the basis of the dice fighter's activity. So in this advanced round function, we're going to first compute the number of hits. So for example, red hits is in the battlefield, it's its own self, red team. We want to compute the hits that the red team has, and we can use some of these auto-completion functions in Spyder to type quickly. We can also write a variable for blue hits to access the blue team in the battlefield and have it compute number of hits. We have red hits and blue hits. And then after those 2 are computed, then we want to have the opposing team suffer those losses. So we'll have the blue team within the battlefield suffer losses from the red hits, and have the red team in the battlefield suffer losses from the blue hits. The last thing that we have to do in the advanced round behavior is simply to increment the round number. So I'm going to access the battlefield round number and simply increment it by 1, using a similar notation before. So the plus equals means take the old round number, add 1 to it, and then assign it back to the same variable. All right. So now if we run the script again, we can test to see that we have the battlefield. Right? And we can try to advance the round from this battlefield. Now if we investigate some of its state variables, so it's, for example, looking at its round number, you can see it's round number 1, which means it's been advanced from 0. We can investigate the red team size, so they are down to 13. And we can also investigate the blue team size. They're down to 7. So it looks like the blue team scored 7 hits in the first round of this game. The red team scored 3. So we could correspondingly continue advancing the round in the console, take a look at the red team size and the blue team size. So in round 2, there's 8 remaining fighters for the red team and 4 for the blue team. But what we really want to do is to automate this advanced round feature so that we can run a complete simulation execution to simulate the all of the rounds in a particular battle. So we're going to do that over here in the script. And we're going to run a loop. So, well, we know that we want to advance the rounds in the battlefield, but we want to keep doing this until we know who the winner is. So we're going to enclose this statement inside of a while loop. And the condition that we're really interested in, so how long do we want to run this loop? Well, we want to run it as long as either the battlefield's red team size is bigger than 0 and the battlefield blue team size is bigger than 0. So as long as the red team size is bigger than 0 and the blue team size is bigger than 0, keep advancing the round. So if either the red team size falls to 0 or smaller, or the blue team size falls to 0 or smaller, then this script will exit out of the while loop and continue executing code down here. So the last little bit of code we want to do is simply figure out who is the winner, and it's a pretty easy check to see. So after the while loop, if the battlefield red team has more than 0, then it's the winner. Red team wins. Otherwise, if the battlefield blue team size is bigger than 0, then we know that the blue team wins. And there's actually a third case, a third possibility. If both the red team size and the blue team size simultaneously fell to 0 or below, we know that we have a tie, that there was mutual destruction. So armed with this script, we can now run this completed version over here in the console. Every time we run it, the script is running through the entire battle process and computing who the final winner was. So we can see, for example, blue team wins, red team wins, red, 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 and blue. If you run this many, many times, you'll generally see, I think that the red team wins about 78, 79% of the time. But to quantify those features more, we'll need to use Monte Carlo simulation.